Okay. So I'll start with question 6. Assuming no one had started that. So we do have this number of electrons flow through a cross section of a 3.7 millimeter diameter iron wire in 5 seconds. What is the electron drift speed? Okay, we do have other people join, so if they have questions ready, that would be better to go over. So, hello for the people who just joined. Do you guys have any question you want me to go over? Jenna or Lee? Really hope that I'm saying your names right. Question 11. Yes. Okay. Okay. So, what's the mean free time between collisions for electrons in an aluminum wire? Huh. Okay. So, let's look. Okay, so just before we start, do you know what equations can we use? I would take that as a no. Okay, so we can just go and look them up. See what equations do we have and what equations they can help us. So the total number of electrons is equal to the electron current multiplied by time. Huh? Makes sense. I don't think we would need that. Okay. What is the mean free time between collisions for electrons in aluminum wire? From where do they give you those questions? Okay, this is the drift speed. Okay, at least we know that aluminum has 6 × 10⁻28 electron density, so that's a good start. Okay, so I just write that down. Aluminum. Okay, so just call this electron density of aluminum is equal to 6 × 10⁻28 electrons per meter cubed. Okay. What else do we have? Okay, so I can find that in section 0.4. It's a good start. Okay, so the J is the current density, okay. And the current density is equal to the number of electrons multiplied by the charge squared multiplied by the time, and that's the time that we need to find. Okay. Okay. I see more now. Okay, so we have resistivity and the conductivity of aluminum. That's nice. Okay, well, just write that then. Okay, so resistivity rho is equal to the mass over NE over E squared times tau. And what we need to find is that tau. Okay, so just rearrange everything, then we would have tau is equal to m over NE E squared and rho. And we have the rho for aluminum is equal to 2.8 10 to the power of -8, where rho aluminum 2.8 10 to the power of -28. Oh, no, it's -8. Oops. Okay. Well, I'm assuming again that this small NE is, let me just check just saying other things. So yeah, tau is, yeah, NE is the electron density or longer times tau between the collisions. So yeah, tau is that what we need to find. Now we need, you can find the electron density from section 27.1 in this table. And the electron density of aluminum is 6 to the power of 28. So electron density of aluminum is equal to 6 to the power of 28. And you're good to go. Just need to check again what is E, because E should be the charge of the electron. Mistaken. Okay, yeah, E is the charge of the electron. Yeah, and the M being the total mass. Okay, well, then you have everything. You have the rho that you need, you have the Ne that you need, and you can find easily the mass of electron and the charge of electron. Oh, you're welcome. Okay, any other questions? Okay, does anyone have any other thing you want me to go over? Okay, well, I was gonna do question 6. Has anyone done question 6? take that as a no. Okay. So yeah, let's try question 6. Yeah, let's question 11. So question 6. We have 2 to the power of 20, so the number of electrons, call that the number is equal to 2 apply 10 to the power of 20 electrons. The flow through a cross section of 3.7 millimeter. So the diameter is equal to 3.7 millimeter of our iron wire in 5 seconds. So our change in time is equal to 5 seconds. And since it told us it's iron, we can also get the information about the electron density in iron, where Fe means iron, from the same table. So we can see what we have and what we need. So the iron is 8.5 to the power of 28. 8.5 to the power of 28 electrons per meter cubed. Okay, so what we need to find is what is the electron drift speed. Okay, does anyone know what to use? Okay, actually, let me write this. So we have this equation, which is the electron current is equal to the current density, electron density multiplied by the area multiplied by the drift speed, which we need to find in here. So equations that we have are equations. We have the electron current is equal to the electron density multiplied by the area multiplied by the drift speed. And we need to find what is the drift speed equal to. What to do?
Are we just gonna rearrange?
Okay, yes. So we're gonna say that VD is equal to IE over NEA. Okay. Do we have NE is here, and we have the A, which is the diameter. We have the diameter of a circle, and you can find the area using the diameter. So, but then what is IE equal to? What is the electron current? Okay, first of all, what is the units of an electron current? What are the units? Does anyone know?
Are we using amps?
Yes, and what are amps are equal to? Okay, so what does current measure? Like when you say you're measuring current, what does that mean? What are you actually measuring?
Is it the number of electrons like passing through per second or something?
Yes, indeed. So current is just the electron flow. So you can represent in a way like the number of charges per second. So coulombs per second. Okay. So now, like the electron current is the electron flow. How many electrons are passing in 1 second? How can we find that? What is that equal to? You just need to check that the electron current is the number of electrons, not the charge. Because there's a difference between the electron current and just current in general. Because current in general is based on the charge passing, but I do believe that electron current is the number of electrons passing. I need to check for that first. Yeah, electron current to be the number of electrons per second. Okay, yeah. Okay, like I also showed you the equation. So what is IE equal to?
Is it the number that they give us in the question, like the number of electrons that flow through a cross section?
Yes.
So it would be the 2 times 10 to the 20.
Okay. Is it that? Is it that's it? Is it just that?
I don't know.
Okay. So this is just a number, but again, the electron current represents the number of electrons per second, like, or the flow of electrons. So you have the number, but just missing time. So what to do?
Oh, use the 5 seconds.
Yes, indeed. So just divided by the delta T over the NE A. And I think you're good to go. You do the same thing. It's just only one question, 2 parts. Yeah, just that. Oops. That I meant to do. And you're good to go. Here you find the electron current, and you have the NE is equal to, and you can just easily find what is the A. So is question 6 okay?
Yes, thank you.
Okay. Any other questions we can go over? It doesn't have that you already did it and you stuck at it. Just like say any question and we can just do it.
You want to do 7?
Okay. Yes. So 7. The mean time between electron collisions in iron is whatever. Okay. So let's do 7. Okay. So from what I saw, that the mean time we can find it using this equation. So I think we're pretty much set here. So 7, we need, is that the question? No, that's not the question. Okay, so yeah, we do have the mean time. Tau is equal to 3.8 10 to the power of negative 15, was it? Seconds. Yes. Okay, so this is our mean time. What electron current is driven through 1.7 millimeter diameter iron? So let's just write that down. Our diameter is equal to 1.7 millimeter. Iron wire by 0.0061 volts per meter electric field. Okay. So we do have our E is equal to 0.0061 volts per meter. Yeah, I add an extra 0. And we want to find what's the electron current. Okay. So again, just using the equation found up here. We can use this one, but I do believe there's another equation we can find. Okay, so the current density is equal to the number of the electron density multiplied by the charge multiplied by the drift speed. That also happens to equal to that. Okay, what again do we have? We have tau, we have the area, and we have the E. We have the tau, but here there's no area we need. So you also need to write what do we actually need to find. We need to find what is the electron current equal to. Okay, express your answer number of electrons per second. Okay, so one thing we do have, you can always find is the electron density in iron, which is also equal to. It's always important to write down what do you have and what do you need to find. So this 8.5 10 to the power of 28 electrons per meter cubed. Yeah, so you always write down what do you have. So when you look through equations, like, yeah, I do have this, I don't have that. So okay, we do have this, we do have that, we do have that, we do have that, we do have that. No, so that's not what we need. Or does it? Or is it, I mean? Okay, so equations that we do have that the electron current is equal to the electron density multiplied by the area multiplied by the VD. Okay, we do have that. We also do have that the VD is equal to here. E tau over M E. Is that right? Yeah. E tau E over M. So that then just means that the electron current is equal to NEA multiplied by the electron charge, the mean time over the mass, multiplied by the. And you do have this, you do have that. You can easily find this, find that, and you do have this, and you do have that. Is that okay?
How are we figuring out the little E and M?
The E and M, like I do believe like the E is just the charge of an electron, which you can easily find.
Right.
And the M, I do believe, is going to be the mass of an electron. Yeah, where M is the mass of an electron. So just to be more obvious what M means, just make it the
Right. So
mass
those
of
are both constants then.
Yeah. Okay, other questions? So is everyone okay with question number 7?
Yes.
Okay. Well, it seems so far like this assignment, it's just mainly, or you need to go and look around for different You need to go around and look for different equations you can use. But then it looks like more straightforward than different assignments. Just 1 second, yeah, looking in.
Could you go over number 19?
Yeah, sure. Just once this opens. Okay, yeah. Oops. There we go. For 19, Kirchenkopf's loop. Yeah. Okay, I'll take that back. Maybe it's not that straightforward. That's gonna be interesting. Okay. So, 19. Okay, so the circuit shown below in figure 1 consists of 4 different resistors and a battery. You don't know the strength of the battery or the values of any of the 4 resistance. Nice. Select the expressions that will equal to the voltage of the battery where delta A, VA for example, is the potential drop across the resistor. Okay. Okay. So, there's so many things going on in 19. It's easy if you know what you're doing. Well, actually, anything is easy if you know what you're doing. So let us just first draw that. Well, can we copy it? That would be epic. No. Okay. Well, that's sad. But it also makes sense why you can't. Okay. So I just draw that. This is the battery. This is the plus. This is the minus. Goes up. Then it breaks to 2 things. One is the other. Am I being recorded? Yeah, good. We have potential difference. We have a resistor D. Go down. We do have D. And we also have here A goes off to B. 2 things, B and C. Then they all connects back. Okay. Okay. This is A, B, C, and D. Yeah. Okay. Okay. So this is our circuit. This is our source. So let's just call it S for now, for source. Okay. So what does Kirchhoff's law says? Like in any circuit, what do you know about the sum of all the potential difference in it? Let me not say that. Let me try a different way. Okay. So yeah, let's start with this. Okay, so this is a battery. Okay, so these, and it's a closed circuit, so there will be current, right? Yes or no?
Yes.
Okay, so from this battery, the current will be go up or go down, or does it matter? Does anyone know? Okay, let's just start by drawing a more simple circuit, and we'll get to that. We'll get to this one later. Just breaking it off piece by piece. Okay, so if this is plus, this is minus. Okay, let's say this battery has a 2 volts, so 2-volt battery. Okay, and this resistor R has resistance of 3 ohms. I want you to find what is the current inside the battery. Does anyone know what to do? I'm assuming they're asking. Yeah.
Are we just doing volts divided by the resistance?
Yeah, because V is equal IR. So that means that I is equal to V over R. Okay. So yeah, that would just equal to 2 over 3. So that's going to equal to 0.66666 ampere. Okay. So this is like more straightforward way to find it. But what we usually do is we will draw where we think how the current is flowing. So usually, since this is plus and this is minus, I know it's electrons that are moving, so it should be coming out of this way, but for historical reasons, people used to say that the current goes from the positive. So we'll say that the current flow this way. Flow this way. Okay? And that current is I. So here we do have a potential difference, S2V. Okay? And we also, okay, then if you have a, like this is a thing. So we call this S being the source. So the V of S is equal to 2V. Okay. Now, for the current passing through a resistance, we know in general that V is equal to IR. So there will be a potential difference around this resistor. Oh, there should be an I in here. Well, you can see the equation there. So there'll be a potential difference around the resistor. So you can say the potential difference around the resistor R just equal to the current passing plus R. Okay? Is a way to find it. Like this is a way to say. Then Kirchhoff's law says just want to say it more correctly. I don't want to butcher it for you guys. Doesn't seem to be here. Well, yeah, that's the sum of the currents. Yeah, okay. Yeah, as I thought. So delta Vs over delta Vr is equal to 0. This is what the law says. So that means that means that Vs is equal to negative delta Vr, which is equal to negative IR. So we have this as in 2V. There's a minus sign I'm adding somewhere. Negative sign I'm adding somewhere. I don't know where is it. Okay, yes, I know. Okay, so if this is positive and this is negative, then we will have this will be positive and this will be negative. So this in itself will be switched the other way. Yeah, if this is positive and this negative, this means this will be the other way around. So it'd have a current going this way. So anyway, like this negative sign, this would be negative. Yeah, and the negatives would go away. Okay. So, okay. Aside from the minus sign I was messing up here, do you get what is happening, more or less? Okay, so Krishenkov's law states that the sum of all delta V's should equal to 0. Basically, that's what it is. So here we do have a potential difference at the battery. And that potential difference, we create a current. And that current would go along the wires, would come here, and we'll also another one we keep passing, comes there. And as the current passes through the resistance would have, the resistor would have potential difference around it. So now each resistor has its own potential difference. So what Kirchenkov says that the sum of all those potential difference around the resistors should equal to the potential difference around of the battery, or like the sum of all of them should just equal to 0. Is that okay? Okay. So let's just start with this. How the current would go. Let's say that the current would go up. once you start with the current 1, this would be the main current going out. Then there's a junction here. And this current would have to break to two currents, one going downwards and one going to the right. So let's call this is I2 and this is I3. Okay. And since the charge of the electric current is conserved, we can say that I1 will equal to I2 plus I3. Is that part okay?
Yeah, that makes sense.
Okay. Okay, so I just keep going with that. So now we have I2. I2 is just gonna keep moving around till it hits D. Then gets back to this junction. So all of this is I2. Right? Okay. So now I3 will be going down, straight down. Then it meets a junction. This is I3. Because of that junction, it would have to split to another two currents. One to the left and one to the right. Let's call this I4. Let's call this I5. Well, again, since I4 and I5 are just coming from I3, we do have that I3 is equal to I4 plus I5. Is that part okay?
Yep, that makes sense.
Okay. So now, just now the I4 keep going down till here. This is I4. Same thing for the I5. Okay, so once they come and meet here at this point, what would be the total current?
It's coming out of B and C is just going to be equal to I3, right?
Yes, indeed, because then it's just, again, I4 plus I5 getting combined together, giving us the I3 that we had before. So here we do have I3. And here we do have I2. So once they meet again, it will give us what?
Just I1 all the way back.
Yes, indeed. Yes, indeed. And that's good, because that means we exit here with I1 and just coming back with I1. So that's good. Oh, I wrote R2, I2. Okay. So is that okay so far?
Yeah, that seems fine, but how do we find the voltage if we don't have any idea what the resistors values are?
Okay. Um. Okay. That'll be the more tricky part. Okay, so now we have I1 in general is just equal to I2 plus I4 plus I5. Enough, we're gonna need that, but we'll see. Okay. So now, we can say that the potential difference on VA will equal to the resistance of A multiplied by I3. Is that right?
Yeah.
Okay. and the resistance, the potential difference around D, so just call it VD. Just be the same thing, be be R of D multiplied by I2. Just keep going on that. So VB is equal to RB, and this will be I4, and last VC is equal to RC for I5. Okay. Okay. This is gonna be more confusing, but I need something that tells you why that's going to be the case. Okay, so just honestly, what was the question? Select all the expressions that equal to the voltage of the battery in the circuits. Okay, yeah. Okay. This is VC. Okay. Okay, so if we did VB plus, okay. Okay, so question, like we do know. Let me draw this here. 'Cause I know what's the answer, but I don't know how to just say it. Okay, so if we do have, this is a resistor, this is another resistor. And here's a battery. Okay, so this is 1, this is 2. We do know if this is S, then the V of S is going to equal to V of 1 plus V of 2, right?
Yeah.
Okay. Because the potential difference just get broken. So break, like, yeah, like get divided to 2 parts, to the part 1 and to resistor 1 and resistor 2, since both of them have the same current. So since they do have like the same current, you have current I going in here. This is I. So then you would have V1 is equal to just the I that you have multiplied by R1 plus the same I multiplied by the R2. So that would equal to I multiplied by the sum of R1 by R2. Okay, so you do have that. So simply, if you want to know what is this Vs is equal to, you can say it's the sum of the V of V1 and V of 2. But if you have the following circuit, and this circuit is called in series, right? Like this is in series. But then you have something else, a different set of circuit, which is called in parallel, where if you have Okay, this is again, this is S, this is 1, and this is 2. You do have, this is I, get broken to I2, and this is I3. This is called just I1.
So if I2 and I3 are both worth half of I1, does that mean like V2 and V3 would be half of V1?
No, that's the
Not
thing.
equivalent like that at all.
No, it doesn't work like that. So
Okay.
the thing is that the currents get divided at the junctions, but the potential difference doesn't. And I'm trying to see how can I show you that. So
All right.
okay, so like here you would just have in this case you would have the potential difference would just equal to Vs. Like if this is 2 volts, you would here have the potential difference is also equal to 2 volts, and here this will be 2 volts. But if here this was 2 volts, and let's say those two were equal, you would here have 1 volt, and here you would have another volt. So 2 plus 2, oh, I'm sorry, 1 plus 1 is equal to 2. But I'm trying to show why is that the case. But just simply, if you have anything in parallel like this, you would have them, both of them have the same voltage. Is that okay?
Yeah, right.
Okay, so if just like you apply the same concept in here, then what can you tell me? What can you tell me about VP and VC?
So B and C would have the same potential difference, right?
Yes. So then VP is what to VC?
Well, it's equal.
Yes, indeed. So just simply that. So now VP is equal to VC. And then since VP is equal to VC, you just like plug it as 1. You can just like call this chunk here as if it's just another resistor, right? And just give it the potential difference of VP. Because the potential difference here would be the same. Like at these 2 points, the potential difference would be the same. So then now we have VA plus VP should equal to S, right? Because here there are 2 junctions. Like, yeah. Okay, so okay, we said that VP is equal to VC. So you can redraw the circuit and just make it more simple now. So this is our battery. Now we do have V of A and another resistor that can represent B and C. Okay, so since the potential difference on B and C is the same, you can just represent the potential difference in one go, like as if it's one thing, right? Okay, so it doesn't seem to be the case. Okay. You do know the potential difference here is VC, right?
Right.
Okay. So the potential difference at these 2 points is VC. Well, what about those 2 points? It'd also be the same thing because like there's no resistance in here. So it'd also be VC.
Right.
Okay. Same thing. What if I just jumped to here? It would be also VC, right?
Yep.
Well, what if like now we jump to this part? It would also be just be VC because the between like if you're going this way, there's no resistance except for C, so it's just VC.
Right. I think I'm more confused about what the question wants. You know what I mean?
So then now just the trick you can ignore. You can just simply say since any two things in parallel they have one potential difference. So you can just put them as one resistor. So then since now we have two potential difference and they are in parallel to this one, you can put them like they would have the same potential difference. So just simply then S is equal to D. Oh, it's wrong. Okay, S is equal to D. This should equal to that.
It would be equal to A plus B plus C as well, wouldn't it?
Okay, let's try that. You mean this one?
I think so.
Well, I say no.
Or I mean, A, B, and C.
A, B, and C. Yeah, yeah. No, I'm sorry. It's gonna be A and C because, like, we know that the potential difference here and here is equal to D, right? So
Oh, right.
A and C would just equal to D, yeah. And also A and B would just equal to D. So there's that too.
Oh, okay. Right. Yep.
Yeah. So yeah, okay, yeah.
Yeah. Well, thanks.
You're welcome. Sorry that was really confusing because I didn't think like
No,
you
that's all
went
right.
over
It's a
that.
weird question, and obviously you can't really just tell us the answer.
Yeah, but yeah, like I didn't know like you already jumped to chapter 28. I still
Yeah.
thought like you were in 27 doing resistance and Ohm's law.
Yeah, it's just jumping around. I don't know.
You guys are going really fast. Like I remember like by this time I was still in
Really,
potential and field. Yeah. So you guys are going really fast. I don't get it.
that's weird. You wouldn't think the online would make us faster.
Yeah, but I don't know.